Hi everybody. In this video, I will motivate a new sort of problem in graph theory by providing some historical context. I'll define some terms involved with this, and finally we'll look at some examples. So the problem we're concerned with here is the problem of Hamiltonicity. So what is Hamiltonicity and what is this word? Well, this comes from Sir William Rowan Hamilton, who was alive in the 1800s, 19th century. Hamilton was a very well-known and renowned physicist and mathematician. So he's a physicist. In particular, one really big result of his was predicting how a ray of light would traverse through a biaxial crystal. And this is what earned him his knighthood. It was such a big discovery once it was experimentally, right? He conjectured, he theorized that a ray of light passing through a biaxial crystal would produce a cone. And then this was experimentally proven, and this earned him his knighthood, and which is why we call him now Sir William Rowan Hamilton. This is one of his big results as a physicist. He was also a renowned mathematician. And this is perhaps where you know of Hamilton, but maybe not. Hamilton invented a new algebraic system. So at this time, the complex numbers had already been discovered. You can think of the complex numbers, right? Complex numbers have the form a plus bi, where I is equal to the square root of -1. That is I squared. Is equal to -1, and there's a multiplication defined on these. These constitute an algebraic structure. What Hamilton did was he was able to extend this to not just 2 dimensions, so you can think of complex numbers like a 2-dimensional number system where products are defined. Hamilton extended this to 4 dimensions and called these are called the Quaternions. So not just a plus bi, but rather a plus bi plus cj plus, let's say, dk. And we can think of these, if you've taken, I don't know, Calc 3 here, you can think of these ij and k as unit vectors in the respective directions. And what Hamilton did really was show that there is a multiplication defined here, and hence that this forms an algebraic structure, numbers of this form. In this case, we have I squared equals j squared equals k squared equals the product of all of these is -1. We have that I times j equals k. J times k is equal to I. And what k times I is equal to j. And what's special about this number system is that so all these things are defined. These help define the algebraic structure. But what's important here is that I times j is k, while j times I is equal to -k. So think about cross products. Really, this is what we now use for 3-dimensional coordinate system, I, j, and k. These are unit vectors, and this multiplication I'm mentioning here is really the cross product multiplication between these unit vectors. So right, ij is in the k direction, j times I is in the -k direction. But it's more than just a 3-dimensional coordinate system. It's actually 4-dimensional when we define our numbers like this. And Hamilton sort of invented this, and there's a famous story where he carves these equations into the wall under a bridge in Dublin, and you can actually go to Dublin and see this, where he first this idea kind of came to him of this 4-dimensional number system. And so in particular, this fact that ij equals k, j times I equals -k, this means it's a non-commutative algebra. And that's kind of a big deal, right? Not many of these were known, and yeah, it was a big deal. So maybe you've heard of the Quaternions. These came from Hamilton. He was the one that invented these. So Hamilton, renowned physicist, renowned mathematician, did a lot of great things. He also had his hand in a bit of graph theory. So this is taking place after Euler and his bridges of Königsberg problem. Hamilton wasn't concerned with that Eulerian problem, but rather a new sort of problem, and it came up in a very interesting way, and that is through a game that he invented. So a little board game that he invented to just for entertainment, and tried to sell this. So the game went like this. There were 20 vertices. So he didn't actually draw his vertices as dots or as points, but just thought of this as the edges and faces of a polyhedra, or polyhedron, I mean. And his question was, in the game, what you had to do was, this was like two-player game. One person picks a point, and the other person has to try and proceed consecutively along the vertices of this polyhedron, visiting every vertex exactly once, following the edges of the polyhedron, and then coming back to where you started. And there were other variations of this. The second player could put more rules on this. There were some other variants of this, but that was the general idea, was to follow the edges of this graph and proceed to every vertex exactly once, and then end up where you started. Now, this game was not a great success. It was interesting, but not a great success. Didn't earn him a lot of money. However, it sort of went into the annals of mathematics, and this is where this problem gets its name of Hamiltonicity, of a Hamiltonian cycle, of a Hamiltonian graph, all comes from this idea of his game. In actuality, a year before Hamilton came out with this Icosian game, Kirkman, who we visited before in concern with trees, Kirkman was doing a lot of problems in graph theory without really realizing it, but had also discovered this problem of, can we take a graph, and of course he didn't use that language, but can we take a graph and follow the edges, proceed to every vertex of the graph, and return to where we started? Which graphs have this property? And in particular, he was looking as well at polyhedra, graphs of polyhedra. So this is the idea. By the way, this polyhedron, if you notice, if you imagine the cycles here, notice every cycle here has 5 edges around it. And so if you sort of blow this up and imagine this as a 3-dimensional object, this is the graph of the dodecahedron. So notice there are 12 faces here, including the outside face. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then the outside face, 12. Once you move this to three dimensions, this outside 5 cycle here becomes a face, and so this is that's 12 sides. So dodeca, that's 12, and so there are 12 faces to this thing. There's 20 vertices on it, hence the Icosian game. That's Greek for 20. There is another Platonic solid, another polyhedron known as the icosahedron with 20 faces on it, but this is the dodecahedron. And so Hamilton made his game around the dodecahedron. Again, can we start at a vertex, proceed along the edges of the graph, hitting every vertex exactly once, and arriving back where we started? This is the problem of Hamiltonicity. Okay, so some terms for this. Let G be a graph. A path in the graph that contains every vertex of G. Remember, so it's a path, and so if it contains every vertex of G, it necessarily contains every vertex exactly once, right? Paths can't repeat vertices. So if you find a path that contains every vertex of the graph, we call that a Hamiltonian path. A cycle that contains every vertex, again, necessarily exactly once, is called a Hamiltonian cycle of G, or just a Hamilton cycle. Some people call this just a Hamilton cycle. And a graph that contains a Hamiltonian cycle is called Hamiltonian. Some people refer to containing a Hamiltonian path as traceable. We won't get into that too much, but we are concerned with what graphs have Hamiltonian paths in them. Primarily, though, we're concerned with which graphs can we find a Hamiltonian cycle. That is, which graphs are Hamiltonian. So let's take a look at a couple examples. Here I have 3 graphs, G1, G2, and G3. And I'd like to determine whether these graphs have these Hamiltonian properties, right? Is there a Hamiltonian path? Is there a Hamiltonian cycle? Is there neither? So let's take a look at G1 here. And if you want, you can pause the video here and sort of piece this out for yourselves, which of these graphs have any of the properties above. Let's see, with G1, can I find a cycle that goes through every vertex exactly once? Yes, I believe I can. I'll trace it out here. And there we have what I just traced out is a Hamiltonian cycle in G1. It encounters every vertex exactly once. And so this is a Hamiltonian cycle, and so G1 is said to be Hamiltonian. Is Hamiltonian. Notice that if a graph is Hamiltonian, if it has a Hamiltonian cycle, well, then it also contains a Hamiltonian path, right? Sort of just delete this from the cycle, and now I have a Hamiltonian path between these two vertices. And in fact, I can do that for any edge of the cycle and find a Hamiltonian path between any two adjacent vertices on the Hamiltonian cycle. So every graph that's Hamiltonian also has several Hamiltonian paths in it. And there might be other Hamiltonian cycles in this graph, but in order to be Hamiltonian, we just need to find one Hamiltonian cycle. Let's look at G2. And again, ask yourself, can I find a cycle that goes through every vertex and encounters every vertex? If you stare at it for a while, you might come up with some argument or some reason why, or just you can't find one. Say that, no, we can't actually find a Hamiltonian cycle in this graph. However, it is possible to find a Hamiltonian path. So let's see, can we find a Hamiltonian path in this graph? So stare at it for a second, for a little bit, see if you can find a Hamiltonian path. So one way you can start to try and find this Hamiltonian path is to realize that these two vertices have degree 2, and so we'll have to take these edges. This will have to be part of the Hamiltonian path. Well, I guess we could not use this edge, right? It could go between those two vertices. We can do a quick check to see that. Let's see. Yeah, let's see. Right, so we can do a quick check here. If you don't have this edge in here, that would mean that these two vertices would have to be the initial and terminal points, and there's not many options for finishing this out. Either way, we take, so we have a choice here of either going down here and then up there, but that would finish the path. We wouldn't be able to return to this as the terminal vertex. We would have missed these vertices, so we can't do that. If we come down here and go do, again, then we've encountered this other vertex too early. We won't be able to use that. And so, yeah, we should have to use this edge between them. That is, these two vertices are not the initial or terminal points. And then we can kind of finish this out. So if I take, say, these edges, that edge there, and then maybe I do the same thing on the other side, exploit the symmetry a little bit. This gives us a Hamiltonian path from this vertex to this vertex. So yeah, why doesn't this have a Hamiltonian cycle? Well, we'll get to that. What's going on here that's preventing a Hamiltonian cycle from occurring? That's a question we'll answer in later videos, later on in the chapter. Let's see, G3 here. Well, look, I have these two vertices of degree 2. So either I have a Hamiltonian path, if I'm just trying to find a Hamiltonian path here. Or I guess, yeah, let's start with Hamiltonian cycle. If I want to have a Hamiltonian cycle in this, I would have to use both of these edges going to that vertex, and I'd have to use both of these edges going to that vertex. So already we can't do this because now I would also have to encounter this vertex that would correspond to taking that edge and this edge, and therefore we would encounter this vertex more than once, and so it wouldn't be a cycle. So there's no Hamiltonian cycle here. What about a Hamiltonian path? Well, we can use similar logic as we did up here. These are degree 2 vertices, and so if I had a Hamiltonian path, well, I don't have to encounter every edge, so yeah, let's see. We could focus on any of these degree 2 vertices. Maybe we look at these two. Maybe we look at these two up here. Think about these. So either our Hamiltonian path goes between those two vertices, so initial and terminal point to this, or they are on the interior of the Hamiltonian path. But any way we do this, so thinking of those two possibilities, any way we do this, we're still going to run into a problem with these two vertices down here, right? I have to encounter, maybe yeah, we should just focus on these two vertices. I have to encounter both of these two vertices in the Hamiltonian path. And actually, we can think about the connectivity a little bit. The fact that if I remove this vertex and this vertex, and it leaves these two then isolated vertices in the graph, that means to get to these isolated vertices, I'd have to go through here and take this one and hit that one, and I'd also have to do the same down here. So we can kind of run through some possibilities and see that this graph is it's not Hamiltonian, so not Hamiltonian, and no Hamiltonian path either. So right, not being Hamiltonian means no Hamiltonian cycle, and then also this doesn't even have a Hamiltonian path in it. This one was not Hamiltonian. It didn't have a Hamiltonian cycle, but it did have a Hamiltonian path. So the principal goal of the rest of these videos is to come up with, just like we did with Eulerian graphs, come up with conditions that guarantee, so sufficient conditions or necessary conditions for a graph to be Hamiltonian. As we'll see, and if you look ahead a little bit in the book, you'll see that we have an entire section just devoted to sufficient conditions for Hamiltonicity, and then we have some other results for necessary conditions for Hamiltonicity. So this is going to turn out to be a much more difficult problem than Eulerian graphs, determining if a graph is Eulerian. There, we just had to look, we had necessary and sufficient conditions for a graph to be Eulerian, right? Every vertex had to be of even degree. Here, there's no such luck. There's no known theorem that gives both necessary and sufficient conditions for a graph to be Hamiltonian. That is, we don't have a characterization for Hamiltonian graphs. So we'll explore sufficient conditions and then also necessary conditions in the later videos. I'll see you there.